All right. So now that we've got that under our belts here, let's come up with a better notation for all of this. So this process that we're doing, this finding the area under the curve, or if the function dips below the x-axis, finding this sort of net area, if you will, right? We add the stuff above, subtract the stuff below, call that a net area, right? What we're going to do is actually we're going to call that a definite integral. So we have some function f of x on some interval a to b. All right. So what we're going to do is create the Riemann sum. The limit as n goes to infinity. Sum I equals 1 to n. F of xi star delta xi. All right. So this is what we're going to call the integral of f of x dx from a to b. Right? And we call this a definite integral. Right? So this will have many important uses, the first of which was just computing these areas. But it turns out what the definite integral does is it gives us a net change in something. Right? So when a function is above the x-axis, we're going to sort of say, something's increasing, it's going up. All right? When something's below the x-axis, we're going to say it's decreasing. Right? Now that turns out to work really well with, say, distance traveled. Right? If we have a velocity function, if it's positive, if it's above the x-axis, the area under that part will contribute to sort of distance traveled forward, whatever we define that to be. When the velocity is negative, we're going to be traveling backwards, right? So we can kind of think of that as negative distance traveled. So if we integrate a distance function over some interval of time, what it gives us is a displacement. In other words, how far from where we started did we get? All right. So let's talk about some properties that a definite integral then has to have. All right. So a couple simple ones here. Let's say properties. Right? So if I integrate the sum of two functions or the difference of two functions from a to b, I can integrate them separately. Oops. This is meant to be a g of x. All right. Now, another thing. If I take a function and I multiply it by a number, it's going to turn out that I can just factor that number out of the integral. All right. That's pretty neat. There's actually a really interesting one here. If I integrate from a to a, f of x dx. Sorry, I was thinking of the next one. This one's mildly interesting. So if I integrate from a to a, think of this in terms of area. I'm trying to say, find the area under this curve over just this point, which there shouldn't be any, right? It's just a line. A line doesn't have area, so this should be 0. Or if you think of it in terms of displacement, how far did you travel between time 0 and time 0? Or time 5 seconds and time 5 seconds, right? None at all. All right, now the actual interesting one here, which is 4, we integrate from a to b of f of x plus b to c of f of x. Think about what this is saying. Right, we find the area from a to b and then the area from b to c, and we want to add them together. It should make sense that actually this just turns out to be the area from a to c of f of x dx. Right? It's a pretty neat fact. Right? One more neat fact here is, sorry, I meant to start this the other way, from b to a, f of x dx. So here we're saying instead of going from a to b, we're going to go from b to a. So if we think about this, what the answer actually has to be is that this is negative of the integral from a to b. Right? And why is this? This comes down to think about how we compute delta x. Right? Instead of thinking of it as b minus a over n, think of it as the top number minus the bottom number divided by n. So if we take, here would be a minus b for delta x. For this integral, it would be b minus a. And those two are negatives of each other. So we get this negative sign right here. So we get these quite nice properties of definite integrals here. All right. So with that, we'll move on to the next topic.